Today, we are diving into the engineering behind a really clever renewable energy solution. It's called Siphonic Hydropower, and it's a technology that could unlock clean energy from thousands of places we already have. And believe it or not, it all comes down to getting one thing just right: the size of a pipe.
So, think about this. There are thousands of dams all over the country that don't actually generate any power. They're just there for things like river control or storing water. Now, turning them into traditional power plants would be incredibly expensive and just a massive disruptive project. So that's the big question, right? How do we tap into all that potential energy without a huge construction job?
And the answer is, well, it's pretty brilliant actually. You don't build through the dam, you build over it. This is a siphonic hydropower system. It's basically a giant pipe, a siphon, that carries water right over the top of the dam. And inside that pipe, a turbine that generates electricity from the flow. The real genius here is that you get to skip most of that expensive, complicated civil engineering work, which means it's way faster and cheaper to get up and running.
Okay, so here's our game plan for how these systems get designed. First, we'll cover the basics of the siphon itself. Then we'll get into the real heart of the engineering challenge, what I call the pressure problem. After that, we'll walk through how to find the perfect pipe, run the all-important safety checks, and finally, look at the finished blueprint for power.
All right, let's kick things off with the basics. What we're doing here is harnessing the potential energy created by the height difference in the water. You can just think of it like a waterfall, but inside a pipe. Engineers call this height difference the head. The siphon's job is to move water from the high side to the low side, spinning a turbine as it goes. Simple, right?
Well, now we get to the heart of the design challenge, because the single most critical decision you have to make is choosing the diameter of that pipe. It's a total Goldilocks problem. It can't be too big and it can't be too small. It has to be, you guessed it, just right.
And here's why it's so critical. If the pipe's too big, the water just kind of meanders through. The flow is inefficient, and you've wasted a ton of money on materials and installation. But, and this is a big but, if the pipe is too small, the water velocity just skyrockets. All that speed creates a ton of friction, which literally sucks the pressure out of the water, creating a dangerous vacuum that can lead to catastrophic damage.
This dangerous pressure drop can cause something called cavitation. The easiest way to think about it is cold boiling. When the pressure gets low enough, the water literally starts to boil, forming these little bubbles of vapor inside the pipe. But as soon as those bubbles move into an area of higher pressure, they collapse with incredible violence. We're talking shockwaves powerful enough to eat away at solid steel, destroying pipes and turbines from the inside out. This is the #1 villain we have to design against.
And this all leads to the central design principle, which comes straight from the Ohio State University research this whole explainer is based on. The goal is to find that perfect balance. You want to pick the smallest, most efficient, most cost-effective pipe you can that will do the job without ever letting the pressure dip into that cavitation danger zone.
So how do engineers actually find that perfect size? Well, they follow a really systematic, data-driven process. A lot of times they'll use a specialized design tool, like the one that was developed for this research. Let's walk through what that process looks like.
It all starts with the site's unique fingerprint. The very first step is to plug in all the specific characteristics. You've got the dam's height, the water depths, even things like the local atmospheric pressure and the water temperature matter. You also make some initial choices, like what the pipe will be made of, because that determines how rough it is on the inside, which affects friction.
So once all those inputs are locked in, the design tool just follows a very clear, logical process. First, it models a whole range of standard off-the-shelf pipe sizes. For every single one, it calculates how fast the water would be moving and how much energy would get lost to friction. Then, it figures out the pressure at the most critical spot, the very top of the siphon. And finally, it sorts through all of that to find the smallest pipe that keeps the pressure safely above that cavitation limit.
Now, what you're seeing here is that process in action. Don't worry about all the individual numbers, that's not the point. The key takeaway is that the tool doesn't guess. It is systematically running the numbers, the physics, for every single possible pipe size, from tiny ones to absolutely huge ones. For each one, it's crunching data on velocity, friction, and pressure, all to find that perfect fit.
And this right here really shows that key trade-off. Just focus on that column for pressure head. See how as the pipe diameter gets smaller and smaller, the pressure drops a lot. Some of those values even go negative, which means you have a vacuum. That is a huge red flag, a clear danger zone for cavitation. The tool's whole job is to find that sweet spot right before the pressure gets too low.
So once the tool has identified what it thinks is the best pipe diameter, the job's not done, not even close.
The next phase is absolutely critical. It's all about verification, making 100% sure the design is safe from cavitation.
This check basically connects the siphon's physical shape to the physics going on inside. The pressure gets calculated at all the important spots, especially at the very crest, using a beefed-up version of a fundamental equation from fluid dynamics. And this isn't some abstract textbook formula. It's been specifically adapted to account for all those real-world energy losses you get from friction inside the pipe.
And you know, good engineering is always conservative engineering. So the tool doesn't just calculate the exact theoretical line where cavitation starts, it builds in a safety buffer. For example, it might add an extra meter of pressure head as a safety factor. That just ensures the system operates well away from the danger zone, even if conditions change a bit.
All of these safety checks get pulled together for what's basically the final exam. This pressure tab compares the calculated pressure at all those critical points against the safe limits we just established. It's the final rigorous check to make sure the design gets a passing grade.
Okay, so after all those complex calculations and all those safety checks, the process finally delivers what we came for: a clear, actionable blueprint for power. This right here, this is the payoff. The Output tab summarizes everything an engineer needs to know. It takes pages and pages of complicated fluid dynamics calculations and boils them all down into one simple, easy-to-read report.
And right there at the top, you get the single most important piece of information: the selected commercial pipe size. In this particular sample calculation, which was for a small-scale model, the answer is a 1-inch pipe. That number is the tangible result of this entire analytical journey.
And right below that, you get the final confirmation. Just these simple yes or no answers that give you immediate peace of mind. Is there a risk of upstream cavitation? No. Downstream? No. Will the system actually deliver the flow rate we need? Yes. It's a clear, unambiguous green light for the entire design.
And ultimately, that's the whole point. This systematic, data-driven approach is what makes Siphonic Hydropower a practical reality. It turns what could be a really complex engineering puzzle into a manageable process. And that lets engineers design these systems faster, cheaper, and most importantly, safer.
And that kind of leaves us with a final thought, doesn't it? This is a brilliant application of physics that's been around for centuries, but it's being applied to a totally modern energy problem. It just makes you wonder, if a simple siphon can help power our future, what other elegant, overlooked solutions are out there, just waiting to be engineered?